Thank you.
Brilliant. Thank you, Rob.
Okay, so I am Patricia Ternes. I am a postdoctoral research working with Nick Manson in the University of Leeds, and today I'm going to talk about how to use an agent-based model with particle filter to estimate real pedestrian traces, and talk a little bit more about the problem with the gate selection, or more generally with the categorical parameters selections. So as my colleagues, I will also use the Grand Central Terminal in New York as my data source for this work. And I am also going to use the STATIONSIM environment for this simulation. But in addition to use the environment, I'm also going to use the real traces for the data simulation steps. So basically, the environment is a rectangular environment with 11 gates, and each agent represents a pedestrian. The general rules are very much simple. The agent just walk in a straight line towards an exit gate. If this movement is not possible, then the agent try to perform some kind of deviation to avoid a collision. And finally, if the agent is in a very crowded situation, then the agent can just wait until the next iteration step. Here, I implemented these rules using a dependence level to control how much interaction we are going to have between the agents. So for each agent in each time, I determined this geographic density, and it's a value between a 0 and 1, and say to the agent how much other agents are around them. This is very flexible for us because we can either calculate this density in each step, or we can just assign some value between 0 and 1, and then make the interaction between the agents in an effective way. So we used this dependence level, or the density value, to control the agent direction of movement and the agent speed. So as I said, the agent tries to walk towards the exit gate in a straight line, but if we found dependence level higher here, we are going to draw a higher deviation angle. Pretty much the same thing for the agent speed. So if you have a high density value here, we are going to decrease the speed of the agent. And if the density is 0, then the agent can walk in a straight line with maximum speed. These two behaviors are related with the parameters of the model. So each agent has 2 parameters, one categorical and one continuous. The categorical parameter is the exit gate and has 11 possible values. So for this model, if you run this model and if you give all possible information for the agents, we are going to have this scenario that I am presenting here. So in the data that we have information from 207 for pedestrians. And we are going to use all information about initial conditions, the speed, and the exit gate in this first experiment. And when we did that, we found 3 different major behaviors for the pedestrian. First, we have pedestrian that performs a linear path. And for us, this is a very good pedestrian because our model is pretty much linear. So our prediction is very good in this scenario. We also have some pedestrians that perform almost linear trajectory, but at some point the pedestrian performs some kind of deviations, probably to avoid some collision. And we can see that our model tries to do the same thing. So the agent here walks in almost straight line, making some kind of deviations, but this deviation is randomly drawn, so we cannot ensure that it's the same deviation that the pedestrian does. And finally, we have the last kind of pedestrian, that are the pedestrian that performs a very complex trajectory. In this situation, our prediction is very poor, even if we give all possible information for the agent. So if we're thinking in terms of our model, we can think, oh, this pedestrian was walking towards a certain exit gate, but in some point, he changed his mind and just go to another gate. And this kind of behavior, the model is not capable to predict this kind of behavior. But for us, it's very good to have this kind of 3 different pedestrian behaviors, because we can answer different questions when we apply the particle filter. The first question is, the particle filter can select the right parameters. The particle filter can correct these small deviations. And finally, what the particle filter is going to do in this when the model is not good enough for the real situation. So before to present to you the particle filter results, I'm just to show what happens with our model if we don't give information about the parameters. As my colleagues mentioned, this is more realistic because we don't have any idea where the pedestrians are going to. So if we don't have information about speed and exit gate, each time that we run the model, we are going to have a very, very different result. And this is expected. And in this situation, our prediction is very poor. And this is the major reason for us try to do some data simulation, because if this result was good, we didn't need the data simulation. So let's look what happens when we apply the particle filter. So I have to highlight here one thing. It's particle filter have the problem of the high dimensionality of this system. We know that. So to avoid this problem, we are just simulating one agent per simulation. The agent still have interactions, but these interactions are effectively and controlled by a density value randomly drawn from a distribution fitted from the data. This approach has some limitation, but gives us some freedom to explore different things. So just have in mind that this is just one agent in the simulation, and when we going to addition more agents, we are going to have the dimensionality problem that particle filter has. So let's look for the complex pedestrian. So I bring here again the pedestrian that makes a complex trajectory, and then we apply the particle filter for this pedestrian. And we can see that in the beginning of the simulation, the particle filter works very well. We have a perfect description of the model, and this is okay, nice. But when the pedestrian changes the behavior, the particle filter cannot predict this changing in the behavior, and the prediction diverges from reality. Okay, so what happens here is that in the beginning of the simulation, particles that have exit gates, different exit gates were sampled out. And after that, there is no comeback. If the exit gates were sampled out, we cannot do anything. And we can see this result and think, okay, I see what happened. I agree with you say, but at the same time, the model is not good. We know that the model is not capable of describing this kind of situation. So maybe the problem is not the particle filter, maybe the problem is the model. So let's move to see what happened when we have a linear pedestrian. So when we have a linear pedestrian, our model is capable of describing this movement. But when we apply the particle filter, we have the same thing. In the beginning of the simulation, we have a very nice prediction. But at some point, the particles with the correct exit gate were sampled out, and the prediction starts to diverge. We consistently observe this behavior with more particles, with different implementations of the model, with more agents inside the simulation. We always observe this kind of behavior. So what I'm proposing here, it's put some additional step into a particle filter. I'm calling this a categorical continuous particle filter, but basically we have the same approach for a common particle filter. I'm just adding this categorical noise step after the update step. So in this categorical noise step, we try to perturb the categorical null parameters. So every agent has a probability of having its categorical parameters defined. The categorical parameter is redefined according to a transition matrix. If you have more than one categorical parameter, we need more than one transition matrix. And this should be applied after the update step, but not necessarily after all update steps. We can control this. So we have three important features here for this categorical noise step work is the redraw probability, the transition, the definition of the transition matrix, and the redraw window here. So how we are going to choose these three values, these three quantities? Well, depends on the model and depends on the data. For the STATIONSIM and the Grand Central Terminal, I am using this transition matrix for the categorical parameters. So it's a little ugly, but let's try to use some examples. So let's suppose that the agent is walking towards the gate 5. This is the exit gate. And we are going to perturb this gate 5 here. So the agent has 40% of chance to keep the gate 5 as exit gate. 25% of change to change for gate 4 or gate 6, and 5% to change for gate 3 or gate 7. 0% in any other gates. So I choose this transition matrix. I could choose any other, but I think this is a first step for us. So what happens when we use this transition matrix with a redrawn window of 100 frames? The other parameters are exactly the same of the particle filter that I presented before. And then here I am presenting some different probabilities, redrawn probabilities. So 0%, we are not going to do anything inside the categorical step. So it's basically the same result for a traditional particle filter. So the dotted line here is pretty much the same result. When we increase the probability by 10%, we can see that we create some kind of variability in the particle set, but we still have some kind of delay between the pedestrian movement and our prediction. The same thing we can observe for the linear case. And when we are going to 50% of probability of changing the categorical parameters, then we can see that our prediction matches with the real traces, even for a very complex scenario when our model was not capable alone of describe this movement. So let's not rush any assumption here, because just increase the probability of change the categorical parameter is not a good idea. It's not enough to have the best possible result. So in this heat map here, I will bring results for several combinations of parameters. The first column is pretty much different samples for the particle filter one. So we have some small fluctuation, but the results are pretty much the same. And they are the worst result between all presented results. So dark red square are high error and dark blue square are low error. So the last line here for 500 frames for the redraw window, we also have a bad result, but this is related with the model, with the data, because at least a half of our pedestrian just stay inside the station for less than 200 frames. So it's important to look at the data and the model to define this value, because we can choose very wrong values for this thing. For the other combinations of values, you can see that we can have, for example, 6.4 of error, or 2.6 is the lower here, but all possible combinations give us better result than just using the particle filter. And the idea here is that we need to create some kind of variability in the particle set, but we cannot create a huge variability because this means very poor particles. So just need to create enough variability to permit different changes in the gate selection. So I'm going to show the result for this square here, so the best result in this image, and a result of a particle filter here in a different visualization, just to match with the first visualization that I showed to you. So in the right, we have the result just for the model prediction, and we can see that just 15% of our prediction were correct. But if you look what happens when we apply the categorical continuous particle filter, now we have more than 60% of our prediction as correct. And if we look just at the traditional particle filter, we can see that the poor prediction increases even when we consider just the model prediction. So the traditional particle filter doesn't work well when we have categorical particle filter, but just with the addition of a simple step, we can improve the results a lot. Again, this was made with only one agent per simulation. We need to follow and increase the size of the simulation, add more agents together and see how we are going to scale. But probably we need to use a different particle filter to couple this additional step, because this bootstrap particle filter is not going to be enough for us. So thank you for your time. If you need or if you want, the presentations are available in my personal web page or the project. And